Hi everybody, in this video I will discuss 4-bit adder subtractor circuit. Subject is digital logic design or digital electronics. Let us consider the designing process of 4-bit adder subtractor. First of all, we have to know what is adder and subtractor. Adder means addition of two binary numbers. It can perform addition of two binary numbers, and subtractor means it can perform subtraction of two binary numbers. We know the addition means normally a plus b, and subtraction means a minus b, that is equal to a plus b bar plus 1. Why a plus b bar plus 1? Because subtraction is nothing but 2's complement of the number. So let us consider the thing one by one. The first point is adder subtractor circuit, adder slash subtractor circuit can perform addition or subtraction. So it is used to perform addition or subtraction, not and. Why we use or? Because when we need addition, then it can perform addition. When we need subtraction, then it will be act as a subtractor. So there is a mode control. Second point is there is a mode control. There is a mode control, capital M. We can name it as capital M, N, whatever. M for mode. Mode control, when that is called mode control M, when M equal to 0, then the circuit act as an adder. When M equal to 0, then the circuit becomes, and the circuit act as a subtractor. Sorry, M equal to 1. M equal to 1 means the circuit act as a subtractor. When we put M equal to 0, the circuit behave as a adder. When we put M equal to 1, then circuit behave as a subtractor. Now let us consider the designing process. Now the third point, that is circuit diagram. When addition mean a plus b, that is equal to 4-bit. In case of 4-bit design, that is the 4-bit adder subtractor. 4-bit adder subtractor. A plus b mean A0, A equal to 4-bit, that is A0, A1, A2, A3, and B equal to B0, B1, B2, B3. So we need just full adder to add those numbers. A plus b, that is sum 0, and there is a carry C1, and the sum 1, there is a carry C2, sum 2, there is a carry C3, sum 3, and finally there is a C out, and in this case Cin equal to 0. For the first bit, there is no need of carry, so consider this Cin as a 0. Now this is the addition of 2-bit number, and in case of subtraction, that is a minus b, we have to perform that a plus b bar plus 1, that is equal to a equal to a0, a1, a2, a3, and b0 bar, b1 bar, b2 bar, b3 bar, and there is a 1 bit addition in the LSB bit. So we have to design these operations. Now we need a 4-bit adder. So the circuit is block diagram, actually logic diagram. This is the 4th point. Block diagram. This is the first full adder 1, and this is the second full adder 2. This is the third full adder 3, and this is the fourth full adder, this is full adder 4. Every full adder has two input A and B, and there is a carry input, that is A, B, C in, and two output, sum and carry out. So every full adder must have 3 input. So in case of this one is A0 remains same, A1 remains same, A1, A2 remains A3. Why it is remains same? Because it directly connect to the circuit. No need to convert them as complement or anything. So here A0, A1, A2, A3. Here in case of this one subtraction A0, A1, A2, A3. So A0, A1, A2, A3 directly input to this full adder circuit. Now in case of addition, there is a mode control. This is the block diagram. See this name here, block diagram. This the fourth point. So there is a mode control. This is suppose this is the mode control. This is the aim. This is the mode control. When aim equal to 0, it acts as a adder. I mean aim equal to 0, it is adder, and aim equal to 1, aim equal to 0, this is adder, and add. Aim equal to 1 means subtract. Now there is a scene. This is the scene. Now when aim equal to 0, this becomes directly 0. Aim equal to 0, when aim equal to 0, then when aim equal to 1, then scene will be the 1. So this is the first bit. Now B0, this is the sum 0 and there is a carry that is equal to C1. This is C1 and this is sum 1, carry C2, sum 3, sum 2, carry C3, and sum 3, there is a carry out. Every full adder must have a 3 input. So 3 input means 1, 2, and there is B input. Now in case of addition, B will be remain B, and in case of subtraction, B will be converted to B bar. Now let us consider how to implement this B and B bar. So there is a XOR gate. We know the XOR table, that is A, B and A XOR B. For the XOR gate, same input, the output will be 0, and the different input output will be 1. So this is the concept of XOR gate. For the same input 0, 0, 1, 1, output will be 0. For the different input 0, 1 or 1, 0, output will be 1. Let us consider the things. When there is a 0, 0, then the next input 0, 1 copy to the output. I mean using these features we can perform the addition. How? I mean when aim equal to 0, that is there is a XOR gate, aim is 0 and there is a B0, and then again there is a aim connected to this one, and this is B1, aim is XOR gate connected to this one, and then there is a B2 input, and finally aim is connected to this one, and then there is a B3 input, and this is the original output of the B after performing XOR operation. I mean when aim equal to 0, that means B0 and 0 XOR operation of B0, first of all 0, write down the 0 and B0, then the XOR operation output will be B0. 0 B1 XOR operation output will be B1. 0 B2 output will be B2. 0 B3 XOR output will be B3. That means when there is a 0 before the input, then 0 help the input to pass through the output. So here the input is 0, aim is 0, and B0 passes to the output. In here B0, B1, B2, B3, and then the full adder act as a addition operation. So this is the addition operation. When aim equal to 0, then this is the aim. When aim equal to 0, so B remain B, B0, B1, B2, B3, and A is A0, A1, A2, A3. So there is a addition operation. Now when aim equal to 1, let's consider this thing. When there is a 1, 0 is complemented to 1 and 1 is complemented to 0. Mean when you put the value of aim equal to 1, then when we perform 1 and B0, then the B0 will be B0 bar. 1 and B1, then after performing XOR operation, B1 will be B1 bar. 1 and B2, the output operation will be B2 bar, and 1 and B3 output operation will be B3 bar. So this is the complement of B. So when aim equal to 1, then there will be A0, B0 bar, E1, B1 bar, A2, B2 bar, A3, B3 bar. And there is a 1, aim, when you press 1, that's 1 goes to the scene. That means A0, B0 bar plus 1, and back remaining all are same. So this is the concept of addition and subtraction operation with the help of XOR gate. So this is the circuit diagram with the help of this one. When we press aim equal to 0, then it will perform addition operation. When we press aim equal to 1, then B will be complemented to B bar, and that there is a C equal to 1, mean A plus B bar plus 1. So this is the subtraction operation. So with the help of the single circuit, we can add or subtract simultaneously. Thank you very much for watching this video. Share and subscribe it.